All right. Good morning, everyone. So this is the third in our series of Google Hangouts on Air to discuss various aspects of EMAN. Now, given the Gordon conference for Cryo-EM is starting in a couple of days, I'm not expecting a whole lot of direct participation this morning, but we'll go ahead and record this for posterity's sake. Today, we're going to talk about... All right. Good morning, everyone. So this is the third in our series of Google Hangouts on Air to discuss various aspects of EMAN. Now, given the... Apparently, I was watching the same presentation that I was giving. Let's give that another try. Hopefully we're still broadcasting. Yes, looks like we are. That was a cool glitch. All right, so I'm in a directory where we've already run some refinements, run various programs in EMAN 2, and I think today's goal is to discuss what some of the output files are in these various directories and how you might look at them, and that'll tell us a little bit more about how EMAN jobs are run. So if we look at the contents of this directory, we see a number of folders in here. We see several refine folders where I've done refinements. That was based on the E2 Refine Easy that we talked about in the first week. Then we've got some multi-directories. These are the results of E2 Refine Multi, which is a multi-reference refinement program which is designed to produce multiple structures from a single refinement job to subdivide data that's heterogeneous in some way. And then we have an R2D01 directory. We also did that previously. That was the result of a E2 Refine 2D job. Then we have the normal directories we're familiar with, the info directory, initial models directory, sets directory, etc. Let's start with sort of the normal processing pipeline, and we'll go through the directories one at a time. So let's start with initial models. Now, I did talk about this briefly previously, but I don't know if I went through each of the different types of files. So if we look in the initial models directory, we'll see that their numbering starts with 00, and then there's a second number which goes 01, 02, 03, 04, etc. The first number is the run number. If you run E2 initial model more than one time, this number will get incremented each time you run it, so it won't throw away the old results. It'll just keep adding new results to the folder. And the second number is the number of the specific model that it constructed. If you remember, E2 initial models is designed to take a few class averages and produce a pretty good initial starting model, which will be enough to get your structure to refine and converge to the correct structure, you hope. So these files aren't produced until the job is basically done because they're produced in sorted order. So in theory, the 01 file should be the best result, and the 08 one will be the worst result. In this case, obviously, I asked for 8 initial models. Now, for each of the iterations, you can see we have 4 different files. The one without any extension, the model 0001.hdf, that's the actual 3-dimensional structure that we produced from that process. In it is the initial model that was used to sort of seed the little refinement process it does when it's producing these structures. That's just there so you can sort of see where it started and where it wound up. Proj are just a set of uniform projections of the final structure that we got, and A particle is a file that lets you compare projections to the class averages that you provided for building the model. I think this is probably easier to look at in the GrowEL example case, so let's go back to the GrowEL case. Okay, so this is a similar directory. So we'll say E2 display, and we'll bring our window up to the front. And now if we look in the initial models directory, if we look at this, we'll see the initial model itself, which was our initial structure of GrowEL, which we then refined to higher resolution. Again, you can see the handedness was wrong, but as I said before, the initial model program, in fact, single particle reconstruction in general, unless you collect tilted data, has no way of determining handedness, so it's a 50-50 chance that it'll be right. If we look at init.hdf, we'll see that the completely random initial model that it generated in this particular case let's see, we'll display just that, look kind of like this, which it has the symmetry that we specified in pose, but it doesn't really look a whole lot like GrowEL. We could take a look at another initial model from one that didn't work so well. So let's take a look at the last one. It should be presumably bad. So we'll look at 08 and 08 initial model, and we'll see that the final, this is the initial model that it came up with, the final result. And obviously there was some problem with this. I think it probably put the GrowEL side views in 90 degrees away from the correct orientation, and this was the starting model it used in that case. So you can see there's nothing really obvious about this starting model being better than that starting model. It's just a different starting point in all right, it appears that the Hangout on Air had a problem associated with it. Looks like we've got one viewer again now. I'm not quite sure when it failed or in what way it failed. Huh, that hasn't happened before. Let's see. Looks like there are a couple of people watching now. All right. Well, let's go ahead and start again, I think. I may have to edit this presentation later on. Okay. So you can ask questions with the question and answer app again now. Let me go ahead and turn on screen sharing again. All right. All right. I'm going to go ahead and pick up with the R2D directories. I'm sure at least a little bit of what I said before had been recorded. So once again, what we're doing today is we're going through all of the different subdirectories that exist and all the files that exist in the various subdirectories after you run the normal EMAN2 refinement programs and looking at what the various files are. So I'm going to start again. If you've already watched the first 5 minutes or something of this and some of it came through, we may have a little bit of repetition here, but again, since I'm not sure exactly where it stopped before, I'm not sure where I need to pick up. All right, so we're going to look in this this refinement directory, and we're going to start with the R2D01 subdirectory. That's the result of a refine2D job. So if we look in this refine2D directory, we'll see a bunch of different sequentially numbered files: aliref, allrefs, basis, classes, etc. Now you should say, well, you should have this documented, right? Somewhere in the documentation it should show us what all of these files are. And absolutely that's true. Whether it shows you in enough detail or not is another question, but we'll take a look at that. So we will go to the EMAN2 wiki, and from the wiki we will browse down to output file descriptions and details. And we'll see here there are a variety of different output files described here. So right now we're talking about 2D reference-free class averaging, so here is at least a brief description of what each of these files contains. Now the description may be fairly brief. There's a little bit more detail on some of the specific types of files up here where it talks about the normal 3D refinement process, and the files overlap with files that are produced when you do the 2D refinement, but there is certainly some information present here. Let's just go back now and I'll describe what we're looking at here. So we need to display and go into the R2D01 directory. All right. Now, these files are produced as part of an iterative process. Each one of the numbers at the end is the end of one particular iteration of that process. When you run a 2D refinement, the first step it needs to do is sort of bootstrap the process and produce some initial rough class averages that it can use to seed the overall refinement process. So that is done by taking the input, making a subset of the input particles. So let's see, input subset. In this case, I had few enough particles. I think it looks like it decided to use all of the particles in the input that I gave it as the initial subset for refinement. So I have my input subset. Those are the files that it's going to use to make this first pass of refinement. And I have input FP. So let's take a look at these FP parts. So these are just particles. Oh, sorry. Wrong directory. There we go. So these are just the particle files that I gave it. Now if we look at input FP, we'll see that we have the same number of images in this file as we do in the input file, the particles file. But of course they don't look anything like actual particles. So what is it we're looking at here? So these images are what we call rotational footprints. Actually, these are rotational translational footprints. They are images invariants under both rotation and translation that are representative of what's in each of the images. In other words, if we took the image of the first particle and we rotated it or translated it in the box, this resulting footprint image should be the same. It shouldn't change based on where the particle is located. And this gives us an easy way of classifying the particles before we have any references that we can use for translational and rotational alignment. The classification we get from this process isn't going to be as good, so this is just going to be used to give us sort of initial classification and guesses. So those footprints are run through a multivariate statistical analysis process, which produces a set of basis vectors. And if you don't know what that means, don't worry about it. You don't need to understand all of that to follow it. It's basically looking at the changes that are present in the various images. So this is, if I looked at those footprint images, this is the average of all the footprint images. And then this image represents the largest differences among the set of images. And the next image represents the largest differences among the set of images, discounting the differences that we've already taken into account, and then so on. So they become less and less significant as we go through the sequence. And let me just take a look and make sure we're still recording, since we had that problem before. Okay, good. It looks like we are still recording. So these are basis vectors in this multivariate statistical analysis space, for which we will then use to classify the initial input particles that we provided. That classification process results in a set of class averages. So we classify the particles. The classification process produces the class MX file. And this is shown as an image file, and it is stored as an image file, but basically it's a 1 by the number of particles dimensions image, and there are 6 images in the stack. So each Y position in the image represents a different input image, and there's only one X value. That X value represents which class each particle was put into in the first image, and then it has other information in the other images. If we go back here, we can actually see there is a classify file. This is one of these classification matrix files, and it tells us what each of the 6 images contain. So the first image contains which class each particle is in. The second image is a weight, which isn't really used for anything right now. And then we have a dx, dy, d alpha. These are translational, rotational parameters to bring the image into alignment. And there's now an optional scaling factor, which isn't being used for anything in this context. So I can show this image, but it's not going to look very interesting. So if I show the image, you can see it's just a vertical line. And if we look in here, each of these the points in this line is a class number for that corresponding particle. If I probe the display or measure the display, if I measure the display, we'll do it that way. I can look at the point values here. So you can see point value 47. So this is telling me the number of the class that each of those particles was in. Once the particles have been classified, class averages are generated. The class averages go into classes underscore 0, 1 iteration number, etc. So in this case, it's classes init. This is the initial set of classes that it made using this bootstrapping procedure. And we can see the initial class averages, and they don't look very spectacular, but we don't really expect them to look very spectacular at this point. The goal is just to get particles which are somewhat similar grouped together. Now you notice they're not very well centered. They're not very spectacular looking in any particular way. Now these are then post-processed to produce the all refs. If I look at all refs 0, 1, these are the same class averages, but now they've been rotationally and translationally aligned to each other and centered in the box, and we can sort of see them in somewhat sorted order. Now they still don't look very good, but again, they don't have to at this point in time. Okay, now the all refs is then processed. The best particles to use as alignment references are then picked from all refs, and those go into align ref. So those are the alignment references. Okay, so these are the 8 class averages that it selected to use as alignment references. So those alignment references will then be used to align the particles for the next round in the iterative process. Okay, so we've got a lie-ref, and we'll then take the particle input, the input stack that was provided, and we will align each particle to each one of these alignment reference images. That will produce the first similarity matrix file. And again, if we look back at the documentation here, it actually will explain the contents of one of these similarity matrix files. Let's see, SimMX. So it'll tell us what the various images are in this file. Now again, this is stored as an image file, but it's really storing sort of matrix information rather than normal image information. Okay, so if we look at the SimMX file again, there's 6 images in this file, and there were 9,978 particles that I gave it as input for this process, and there are x equals 8 in this case. Why is the width in the x dimension 8? That's because I have 8 alignment references. So each x position in this similarity matrix file represents one of my alignment references. So if I show the first image in this stack, again, we'll see it's just this long vertical stripe. If I look at one row in this image, what I'm seeing is how similar that particle was to each of the 8 different references. In this case, based on the standards in EMAN 2, smaller numbers are better. Smaller numbers indicate more similarity. So for example, if you look at this row, that means that that particle looked a lot more like the 5th reference than it did any of the other references. Now, this isn't being used for classification in this case, and we use almost an identical process for classification when we're doing 3D refinement. In this case, it's being used just to get the 2D alignments right, so we can run the multivariate statistical analysis again. Okay, so this file is not being used for classification, it's just being used to get the correct dx, dy, and rotational angle for each particle. Okay, so once we've finished running running that process, we go back and we run the multivariate statistical analysis again, which now gives us a new set of basis vectors. So now we'll see that the basis vectors actually look more like particles instead of like those funny footprint things we had before. And you can see in this first round, these basis vectors don't look all that interesting because we still don't have very good classification on our particles yet. If we look at one of the later rounds, hopefully we'll see a lot more structure in these basis vectors. Okay, and you'll see that we start out again with the average of all the particles. Remember, we're looking at a ribosome here, so this isn't GROEL. You shouldn't expect to see any GROEL-like features. And what you'll see is the coarsest sorts of features in the first few basis vectors, and then as you proceed to higher and higher numbered basis vectors, you'll see finer and finer features, and eventually it'll degrade into noise if you let it go far enough. Now, for this process, we normally only keep on the order of 10 or 15 of these basis vectors because that's enough to do the 2D classification we're trying to accomplish. All right, now these basis vectors are once again used for classifying the particles. So again, we get another one of these class MX files. If we could look at the class MX file again, but it's just a vertical line with class numbers in it. It's not all that interesting to look at. Then again, we get another set of class averages. So let's look at the end of the process now. So this is what the final class averages look like. They're reasonably well centered in the box now, even without that final alignment process. But with the final alignment process, we should see that similar ones are adjacent to each other in the output file. It's not going to be a perfect process. For example, for some reason it decided this one looked more similar to that than this one did. To me, by eye, I would say this one looked more similar to that one, but there's obviously something present in this image which made the similarity come out closer. In any case, they should all be pretty well centered, and they should all be in about the right orientation. So normally, when I'm trying to find the output files from a 2D refinement process, I will look at this allrefs file, which will normally be sorted and in a more convenient order to look at. Although classes is also an accurate representation of the output from the process. Okay, let's see if we had any questions about that. You're welcome to ask questions too. Yeah, this is ribosome data. So we have one person present in the room right now as well. All right. So that finishes the R2D01 directory. I'm going to go. Well, I think I discussed initial models pretty well in the previous tutorial. I don't want to go back and do it again. Some of it was probably already recorded this morning, so I'm not going to go back and redo that one again. If you have any questions about the initial model output files, feel free to ask them or email them to me later. Okay, the next directory we'll take a look at then is one of the refined directories. So we again looked at one of these previously. But let's look at the files in a little more detail now. Okay, so as we discussed previously, the final output of the process is, of course, these 3D files. 3D05, for example, being after 5 iterations of refinement, that's the final average between the even and the odd structures. Now, in EMAN 2.1, we use the gold standard refinement processing. What that means is when you start your refinement running, it will split your input data up into 2 groups, and all the even-numbered particles in one, and all the odd-numbered particles in the other. The reason we use even and odd is because that way we have basically the same number of particles from each micrograph, and we don't have any funny biases due to that. And whether the numbering of the particles should basically be random anyway, so hopefully that'll give us a pretty good random distribution. Now, it's not enough to just divide the data up into 2 groups. You also have to make sure that the 2 different subsets of data aren't seeded with the same initial model, otherwise you can get model bias problems. Now, EMAN and refinement, which is the only other package that I'm aware of right now which does gold standard refinements as a matter of course, do this in a slightly different way. So in refinement, the typical method is to low-pass filter the input volume such that it doesn't have any information at all past about 50 angstroms. So all the high-resolution information is completely wiped out. But then you use the same input model for both of the two structures. It's just that since there's no high-resolution bias, it's assumed that if you pull out any high-resolution information, it'll be different. I was concerned about the fact that you're basically starting at the same place. You're starting with the same starting model even if there isn't any high-resolution information, and that worried me that we could still have some model bias. So the procedure we use is a little different. Instead of zeroing out the high-resolution information, we actually leave the high-resolution information from our initial model in there, but we completely randomize the phases past a resolution which is much lower than the resolution that you're targeting. So if I'm targeting, say, 10 angstrom resolution, I'll say anything higher resolution than 20 angstroms, I will randomize the phases. So this is a much more stringent test. It not only it doesn't just wipe out the high-resolution information, it actually leaves signal in there, but randomizes it, so the structures are completely terrible. So let's take a look. Let me go back to GROEL just because it's easier to visualize sort of what it's supposed to look like. Oops. There we go. So here's a GROEL refinement directory. Now, if we maybe I should start with the first refinement. Now, if we look here, we'll see 3D00 even and 3D00 odd. So 3D01 is the result of the first round of refinement. 00 is the input model that was put in for both the even and the odd sets for each case. So if we look at these two, what we should see are that they are, oops. There we go. Is that they are different in any high-resolution features. Now, the input model I gave it was already pretty low-pass filtered, so it didn't have a whole lot of high-resolution signal there in the first place. But any information that was there, for example, you can see there is some high-resolution noise present there. Maybe we'll do that on this one too. Oops, went too far. There we go. Now if we switch between those two, you can see all the high-resolution noise that's present in there is completely different. And these structures are actually pretty different all the way out to sort of 20 angstroms. So our two starting models are starting from very different places. So if, despite that fact, they still converge to the same final answer, then we can be very confident that the data really represents only one structure. That structure is self-consistent and gives us the same answer. So then if we look at the final even and odd maps, we can then visually detect the differences between that are resulting in the resolution value that we're getting. So now let me switch out to the 2 and 3. Let me zoom in here. Okay. So this was the odd final map, and this was the even final map. And now you can see why the resolution was limited to the resolution that it was limited to. So in this case, it was about 8 angstrom resolution. Actually, this was an initial refinement, so it may actually be a little worse, 10 or 12 angstrom resolution. So we can see at the level of the alpha helices in here, there actually still are some discrepancies there. So what the refinement process does is computes an FSC between the even map and the odd map. Then it uses that FSC to filter the final 3D volume, which is the average of the two. So if we look at 3D04, that's the average of the even and odd maps after a filter has been applied, so we don't see any of that residual noise, right? So there's the even, there's the odd, and there's the average between the two. Okay, even, odd, average. Okay, so that's the overall process that's involved here. So those are just the 3D output files, but this, as you noticed, a bunch of other files in here. Now, some of these will look familiar from the 2D refinement directory that we were looking at a few minutes ago. So we see, for example, a class MX file. We see classes files. So what's going on here? So the way the refinement process goes is we start with some sort of a 3D structure, and we make projections of the structure. Okay, so I see I have my projections files here. And again, everything is split even and odd here. So we have 2 projection files for each iteration. The number of projections is determined by the angular step, and that in EMAN 2.1 is determined for you automatically, although you can override it if you feel you need to. So let's take a look at these projections. So here's the projections of the initial model. You can see there's some noise in the background here. If I switch quickly, keep an eye on the images, and I'm going to switch to the odd projections. You can see there are some differences between the even mod. Those are the differences between the initial model, between the 2 different initial models after the phase randomization. So there are some subtle differences there. All right. So these are the projections. Pretty straightforward. Now, when we do the classification of each particle, one way we could handle it is we could just compare every particle to every one of those projections. And with only 30 of them, that probably wouldn't be too terrible. Let me go back now, though, to the ribosome project. And if we look in the refinement in the ribosome project, we'll see that we actually have a lot. We have 290 projections here. That's because we don't have any symmetry. Now, this is still a low-resolution refinement. If you're going for a high-resolution structure and you don't have a lot of symmetry, you can easily wind up in a case where you have 2,000 or 3,000 projections. Now, the question is, does it make sense? For example, here's our set of projections. Does it make sense when I'm trying to determine the orientation of the particle to compare the particle against this and this and this, and to compare against this and this and this, or could I compare it against some representative indicating orientations close to this orientation, and then sort of fine tune it? Could I do it hierarchically instead? So that's the actual process that we use. Now, the problem that you get if you try and do it hierarchically is the fact that the appearance of the particle isn't necessarily uniquely related to the orientation of the particle. It's possible to have a particle in one orientation and another fairly distant orientation and actually look somewhat similar to each other. So in EMAN 1, we actually had an approach where we based it on geometry, and we said, here's our unit sphere, we have projections represented as points in the unit sphere, and we just sort of clustered them by, geometrically, by looking at points that were close to each other in the sphere, and then hierarchically classified things. It worked okay, but it never really worked very reliably, and we never used that for high-resolution refinement because it had some issues with it. So we actually have a 3-step process now that we do in EMAN 2.1 to get around that problem. So the first thing we do is we compare all of the projections to each other. So rather than comparing particles to projections, we're comparing projections to other projections. So we generate a similarity matrix, which is just like that SimMX file we saw before, but this similarity matrix is comparing projections to projections. So if we look, let's see, here we go, proj SimMX. So you can see this file is 290 by 290. So the dimensions of those matrices correspond to the number of projections I have. So if I open up this file and look at the first image, oh, sorry, I should do it a different way. Let me look at it in 2D. There we go. And I look at the first image, what I'll see is basically a visual representation of a similarity matrix. So all of the x-axis are each point on the x-axis is a projection, and each point on the y-axis is a corresponding projection. So we expect this matrix to be pretty much symmetric. And as we also would expect, along the xy diagonal, we see a dark line. If you remember, I said lower values, darker values indicate higher similarity in EMAN 2. So regardless of the similarity metric used, if you say a dot product is a similarity metric where you'd expect 1 to be good and -1 to be bad, whenever we use a similarity metric like that, we invert it. So the dot products are all multiplied by -1. So -1 indicates perfect correlation and 1 indicates 0 correlation, just to obey this convention. Because there are other metrics, for example, the RMS deviation between a particle and a reference where smaller is better. So we had to pick one convention. Is smaller better or is bigger better? And we picked smaller. Okay. So smaller is better. So that means that the particles agree with themselves very well. So the projections agree with themselves very nicely, as you would expect. And then we have another little stripe across here. This indicates where we have stepped up one step in azimuth. So if we take a look at the distribution of particles in orientation space, let's see, let me run a different program here. Unfortunately, this program I think isn't available from the GUI at the moment. Yeah. All right, so I'm going to run a program called E2 Euler Explorer. And this program allows us to look at the distribution of orientations of particles that we got in a project. I didn't talk about this last time, although I probably should have. At least I don't think I talked about it last time. So now we see this unit hemisphere, and we see these lumps. Oh, maybe I did show this last time. I think I showed how you could compare class averages to projections. Okay, so if we look at a point here, we'll see in a couple of different windows, we'll see this is a projection, this is a class average that's been filtered to make it match the projection, and then this is the original class average. And the same thing in this window, we can see the three different images and compare them. Anyway, that's not the point of what I'm talking about now. What I want to show you here is, say we have a projection here and a projection here. So you can see these projections run, and this was done with an older version of the program, so you can see the projections aren't sort of uniformly distributed, they're kind of randomly moving around. That's something we used to do frequently, but we've pretty much stopped doing it in the current versions of EMAN, because now that we're doing gold standard refinements, it's not as necessary. In any case, they still run roughly in rows. So you can sort of see horizontally here, there's a row, and then there's another row. So the way the projections are generated is they start at the top, and then they go to the next row, and then they go to the next row, and then they go to the next row, etc., sequentially. So the stripes that we're seeing in this similarity matrix, lost it, are moving from one row to the next. So up here, this is 0, 0. This corresponds to the top view, and there aren't very many particles in each ring around the top view. But as we get close to the side view, there are more and more particles in each ring. That's why these stripes start close together, and then they separate more and more. So this is showing us that the particles are very similar to themselves, the projections are very similar to themselves. They're also pretty similar to the projections in the next row, one sort of Euler angle step away. And they're also similar, but not as similar to the ones in the next row, et cetera, et cetera. So this is just indicating sort of the geometry of the projections that we're generating. So now that we've determined how similar the projections are to each other, what we're going to do is we're going to classify the projections. We're going to take each projection and find the n other projections that it looks the most similar to, and then we're going to average those together and make these sort of average projections for particular views. Not necessarily defined by geometry, just defined based on how similar the projections are. So when we've done that, all right, so let's see, we had our projections. Then we were talking about the projection similarity matrix, which allows us to classify the projections. Then we have the projection stage 1 file. These are the average projections, which are used to first classify the particles. And then we do a second stage classification where we determine the precise orientation of each of the particles. So if we look at one of these files, we'll see now we only have 50 projections instead of 300 projections. And you can see they're still pretty homogeneous looking. They're a little fuzzier looking because we've averaged together multiple orientations, but they're still pretty good. Now, you'd say, how many should I expect to see here? So you can see I've got 50, and I had 300 projections. It seems more like I should be able to do something kind of like, the square root of the number, or the log of the number, or something like that, if I'm going to do hierarchical classification. And indeed, that's what happens. We're doing something like that, but we don't think it's trustworthy. We don't think you can trust the answer if we just classify each particle with the one orientation that it looks the most like. So what we do is we take each particle, we find several, I think it's 4 typically, orientations which it looks the most like, and then it takes the fine projections associated with all of those different orientations. So rather than, so we can't subdivide it quite as much as we'd like, otherwise we sometimes get the answer wrong. So we're doing a little bit of sort of oversampling in projection space. We're sampling a little bit more than we really would need to on paper, just to double check and sort of make sure that we're really finding the right orientation. So if we have 300, it goes down to a number something like 50. If we have 5,000, it will still get down to a number something like 100 or 200. So this is a algorithm which gives you more benefit the larger the problem is. So if you're doing a really small refinement, if you're doing GrowEL on your laptop or something like that, you may go from 100 projections down to 30 projections or something. It's going to save you a factor of 2 or 3 maybe, but it's not going to save you a really large factor. If you're doing something like a ribosome at 3 angstrom resolution, however, and you've got 5,000 projections, it's going to save you maybe a factor of 20 or 30 in time. So you gain more and more benefits the bigger your project becomes. All right, so this is the stage 1 comparison, the stage 1 references for comparison. Then if we look at SimMX down here, we'll see there are 2 SimMX files. There's a SimMX stage 1 file where it's comparing each particle to each of the 51 first stage references. And then we have a normal similarity matrix file where it's comparing each particle to only the subset of the references that were determined by the first stage classification. So if we look at this similarity matrix file, it's got the full dimensions. It's 290 by 5,000, which is half of our particle population. But let me do it the other way. But you'll see that a lot of the values in here are just constant values. There's only a few places where we see dark along each line. So what we're seeing is wherever you see dark, those are orientations where it specifically did a comparison with the fine, with one of the detailed particle orientations, one of the detailed projections. Any place where you see this sort of white line, white streak, is a place where it didn't have to sample that orientation, it could ignore it. So you can see in each line, it really doesn't have to do very many of these similarity comparisons at all. So we're saving probably, well, you can tell, from 290 down to 50, so we're saving about a factor of 6 here in computation. Anyway, so the only goal here is we want to find the darkest pixel along each one of these lines, which of course represents the correct orientation. And that produces the class MX file, which is the classification file, just like it was when we were looking at the 2D refinement. Let me take a look and see. Well, we've got a few people watching, no questions posted, so we'll keep going. All right, so the classification matrix file is exactly like before. It is 1 by the number of particles, and that tells you which class each particle went into. And then that information is used to generate the class averages for the even and the odd populations. If we look at one of these sets of class averages, we can see we have the same number of class averages as we had projections. And hopefully the class averages look similar to the projections. I can compare them. The way I usually compare them is by showing a class average file and then double-clicking on the corresponding projections file so I can switch between them quickly and sort of see how well they compare. But we could also use that E2 Euler Explorer tool that we were using a few minutes ago to compare the projections to the class averages. Once I've got class averages, I then take the class averages and I do a 3D reconstruction. That produces the 3D 05 even, 3D 05 odd, sort of. Actually, what it produces is the 3D even unmasked and 3D odd unmasked. Then these two files are post-processed. They're low-pass filtered, which allows us to produce a mask. Then the FSC is computed, which allows us to compute a filter. And then we go back and we sort of clean them up a little bit. So the final files that we get in even and odd aren't the original results of the 3D reconstruction. They've been masked and filtered a bit. For the final iteration, we keep the unmasked version of the file in case you want to run some resolution test or something that requires having unmasked data. But we only have that for the last iteration. Right. There's one other file I guess we didn't talk about in here. There's the CLS result file. So we have the class MX file, which contains the classification information. Then we also have the CLS result file, which has the same dimensions. So what this is the final orientation of the particle after making the class averages. So we have the orientation of the particle that we determined when we did the alignment to the projections. But then we have an additional step where we align the particles to each other iteratively. When we make the class averages, the particles are allowed to diverge from that orientation that it was determined based on the projection, and they are allowed to agree with themselves rather than agreeing with the projection. This actually can make the overall refinement process converge much more quickly than it would otherwise. If you look at, say, a refinement in Spider or something like that, where you just do a direct comparison of the particle to the projection and then put it in that orientation, do reconstruction, you may have to run 30 or 40 iterations before the process converges. By allowing the particles in similar orientations to align to each other and make these class averages, we can speed that process up dramatically. So once it's sort of adjusted the 2D alignments of each particle, those adjusted orientations are stored in the CLS result file, which contains not only classification information but also 2D orientation information. Okay, what other files do we have here? We've talked about most of them. So we haven't talked about the mask file. The mask file is just the three-dimensional mask that was applied after being automatically generated in the... So it uses that actually in the 2D refinement process. Oh, actually, sorry, that's sim mask. Sorry, that's a projection mask. Sorry. So this is a two-dimensional projection of the mask, which is then used when it's doing particle classifications optionally. It allows you to exclude some of the noise in the volume when it's doing the particle alignments and classifications. Mask is actually a three-dimensional mask, which we have to pick a decent threshold, which shows you how the final 3D volume was masked out, auto-masked out. Okay. Let's see. We have the FSC curves, and these are the FSCs between the even and the odd numbered output particles. So FSC masked is, of course, the FSC with a mask present. The FSC unmasked is the FSC before the mask was applied. So we can look at the FSC masked, and we can look at the FSC unmasked, and we can see that they'll generally have basically the same shape, but the unmasked version will be a little bit lower because it's including more noise from the edges in the box, that sort of thing. So this is not a very high-resolution refinement here. This was just a few ribosome particles that were being refined. We wouldn't expect it to get to very high resolution. It was also a heterogeneous population, and that's the next thing we'll talk about.
Yes, the sum map has been generated independently.
The which map?
Sum map has been
Make
3D.
Make 3D is done independently for the even and the odd data halves. Yes, everything is done completely independently for the even and the odd refinements. The only way they see each other at all is after the 3D volumes are computed. If you don't have any symmetry to anchor the orientation, the one 3D volume is aligned in 3D to the other 3D volume just to keep them in the same general orientation, so when you do the resolution measurements, they come out correct. But that doesn't affect its shape or its structure in any way. It's just changing its orientation. If you have symmetry like icosahedral symmetry, that anchors the orientation and you don't have to do it. Yeah. So basically, those two refinements are done completely independently from each other. Okay, I think we hit all of the file. Oh, sorry. There's the refined parms.json file. That can be useful if, for example, you want to compare what you did between two refinement directories, or if you want to know the exact options that you used in that refinement. You can always go back and look at the command that you ran, of course, but this will tell you the exact parameters that were determined. So if I click on that, if I hit info, I can see all of the command line parameters that were passed into the refinement program. Now, these aren't necessarily values you provided. So, for example, pad is not something that you need to provide anymore. It determines that automatically. But all of these parameters could be overridden from the command line if you wanted to. So if you see some parameter that it picked here that you think is not the correct choice for your data set, you could then go back and rerun the E2 Refine Easy and specify this additional option with some different value, and then it would override the automatically determined values. And as I mentioned last time, we have this report directory which contains this HTML report which tells us about the refinement and why it picked the parameters that it picked, that sort of thing. Okay, think that's it. Let's see if there's any questions showing up. Okay, no questions. All right. One more type of directory we'll take a look at in this project, and that is the multi-directories. So there's another refinement program called E2Refine Multi. It's similar to E2Refine Easy, but in this case, instead of just refining one initial model, it refines multiple initial models. So you give it, say, 3 or 4 or 5, whatever you like, starting models, and it will simultaneously refine all of them. Now, there's no gold standard refinement done in this case because you're already splitting your data up into multiple groups for the multi-model refinement. So once you finish segregating your data based on a multi-refinement process, you then need to go back and take the particles that you got out of each of those processes and run an E2Refine Easy on each of those to get a gold standard resolution for the subset of data. So a case where you might want to do this is, say this ribosome project I'm in. This ribosome actually has a channel associated with it. So this is a heterogeneous particle population. Sometimes the channel is there, sometimes the channel isn't. And it's about, I think, 60% of the time it's not there, and 40% of the time it is there, something along those lines. So the idea with a multi-model refinement is I would give it 2 starting models. Perhaps one where so first I would start by running a normal refinement. I would get my structure out, and I would find where this extra ligand is. Then I would manually exclude the ligand, in this case the channel, from one of the volumes. So then I would have 2 reference volumes. I would have one reference volume that has the channel, although it's kind of weak because it wasn't present in all the particles, and then I'd have another subvolume where I manually wiped out the channel. Then I could run a multi-model refinement where I use 2 different references, one with the channel, one without the channel, and then the particles would hopefully segregate them into 2 groups, one set of particles with channels and one set of particles without channels. Now this process isn't absolutely perfect, and there are other programs like E2 Classify Ligand which can be used to maybe do that particular process more precisely. But if you're looking at more sort of continuous heterogeneity, some molecule that moves and has dynamics and stuff, you may need to subdivide it into, say, 4 or 5 different groups, and there may be broad dynamics across the whole structure. And in that case, the multi-model refinement is definitely the correct answer. So let's take a look at what we get in a multi-model refinement. All right. If we look at the contents of this directory, it's going to look very, very familiar. Again, you're going to see projections, you're going to see 3D files, we're going to see SimMX files, classes, class results, etc., etc., etc. So what's going on here? Now I've got multiple input models. So if I look at 3D00, you can see in this directory I use 3 different input structures. Let's go ahead and open those up. Now there's no phase randomization here because, again, we're not doing gold standard here. We're just trying to subclassify the particles. So we want to have model bias in a sense in this particular case. So if I scroll through these, I can see my 3 different. Now these starting structures were generated randomly by dropping chunks out of the structure. Okay, so there's a mechanism where you can specify that it should do that. You give it 1 reference model, and you tell it to automatically randomly perturb it for you. And this is one of the ways it'll do it. So we start with the first model, which is basically the whole thing. Then the second one is missing a big chunk, and then the third one is missing a different big chunk. It's just designed to sort of explore what might be going on in the structure a little bit by seeding it randomly. So anyway, those are my 3 different input models, and then for each iteration, I have 3 different output structures. Okay, so it's just like the even and odd case, but instead of having just even and odd, I can have n different output models. Could be 5, could be 10, whatever. Now, you'll notice in the classes files, I don't have 3 different classes files in each case. I only have 1 classes file. In the projections, I only have 1 projection file. So the way this is handled is, if you look in the projections file, we'll see that we have 3 sets of projections in the same orientations, basically, sequentially in the file. Okay, so I have 1 set here, and then if I look a third of the way through the file, I'll see the same orientation coming up here. So this 833 is in the same orientation as 0, but it's for the second reference volume. So if I have n reference volumes, I will have n times the normal number of projections in my projection file, and all of the references for the first projection go together, then all of the references for the second projection, then all the references to the third projection. Now, when I'm doing this multi-stage classification I talked about before, in the case of a multi-model refinement, I actually get an extra little benefit out here, because this is definitely a case where two particles in similar orientations are not going to be the most similar to each other. So now I have multiple input models. So if I have multiple input models which are pretty similar except for some perturbation, then I would expect the same orientation in the three different input structures to look almost exactly the same. So by putting all my projections into the same file and then running this multi-stage refinement process, I will then group together whichever projections look the most similar, and that may be from different models into the same projection, and that helps me avoid biasing my refinement into one associating with one model versus another model. So again, I'll have all of the same things here. So everything works basically the same way as it does with a single model refinement. My projections represent multiple models, and the metadata for each of those projections indicates which one of the three, in this case, structures it was associated with. So when I get class averages, I will have class averages for each one of the three different sets. And you can see there are some gray ones that indicate there were no particles found to be in that orientation. And that's because I have 10,000 particles and I've got 2,500 projections. So if any class average has more than 4 particles in it, then I'm going to have some class average that's missing some. Okay, so I'll see all of my class averages for all of my reconstructions there, and then the Make3D program will go through the class averages and sort out which one is associated with which structure and build the corresponding 3D volumes. Now there's also a report directory here. The report for this program hasn't been fleshed out as much as it has for E2 Refine Easy. We just haven't gotten back to it again yet. But as time goes on, we'll see that report improving as well. Now, the next thing you'd need to do after running one of these multi-model refinements is, as I mentioned before, run a gold standard refinement with E2 Refine Easy on the subset of particles. How do we get the subset of particles out? Now, in EMAN 2.0, there was a program that we used called E2 eval particles, which still exists and still can be used for that purpose if you want, but it's not necessary. E2 eval particles allows us to look at any classes file that we've generated and see which particles went into which class and pull them out into smaller subsets and stuff, mark bad particles, that sort of thing. So if I pick this classes file, for example, I'll get these 3 windows popping up, which are black at the moment. They should be. Okay, so here's the classes. If I click on one class average, it will show me the particles, the good particles that were included in the class average, and it will show me any bad particles from that class average. There weren't any in this particular case. So I can pick any particular class average I like, and it'll show me the corresponding particles. If I double-click on a class average, it will mark that class average for some other operation I want to do over here. I could also select ranges, for example. So the way you used to have to do it is I would say, oh, I've got 832 class averages associated with the first model. So I'd say range, and I'd select 0 to 832. And now all of those are going to be marked here, but the later ones won't be. And then I would say, okay, I want to make a new particle set, and that would pull out all the particles associated with those 832 class averages, et cetera, et cetera. You don't have to do it that way anymore. Now, when you run E2 Refine Multi, if I look in the sets directory, I will see that after it finishes running the multi-refinement, it will automatically generate subsets for the particles for each of the different classes for me. So I will now see for the fourth. So this is the fourth multi-refine run. So this is multi-O. Let's see. So we have multi-04. So when multi-04 finished, it made these 3 files: mul04, M1, M2, and M3. So these were the files from the 4th iteration of multi-refine 04, and these were the particles that were associated with model 1, model 2, and model 3, and then I can just directly use those as input files for E2 Refine Easy. Now, you'll note I don't have output files for all of the different multi-refines I ran here. So what happened? what happened is I didn't let all those multi-refines finish. I started them running and I decided something was wrong and I stopped it, but I didn't delete the multi-refine directory or something. These are only generated after the final iteration completes. Now there is a program that exists that you can use to generate these manually from a multi-refinement. Say the multi-refinement didn't finish, but it converged far enough, and you want to still generate these files. There's E2, I have to remember the name. I thought it was E2 extract or something, but maybe E2. See, even I don't remember the names of all the programs.
E2 classes extract.
Classes extract. Thank you. Thank you, Zhao. Right. So there's E2 classes. Class extract. There we go. And we can see that this will allow me to specify an E2 refine multi-directory, and then I can specify a subset from that, and it will then generate all of those classes files for me. So then I would end up with additional sets files in there. All right. Well, we've gone for an hour, and I think we've covered the major output files from the major programs. So I think, let's see if there's any questions that showed up. Okay. So I think we'll probably stop there, and we won't have another one of these sessions next week because the Cryo-EM Gordon conference is next week. Hopefully I'll be able to resume the week after the Gordon conference, but I'll post more on the wiki about the wiki and my YouTube channel about whether we're going to continue that week or when the next one is. Thanks everyone for joining in.